Hello, in this video we're going to talk about absolute and apparent magnitudes and answer these two questions. What is the apparent magnitude of the sun and the moon? And then what is the absolute magnitude of the sun compared to a supernova? So this picture is of Hipparchus, and I'm sure I'm butchering his name, but basically he looked at the brightest star in the sky at his time and labeled it 1. And then he took the faintest star and labeled it 6. And then the spectrum in between, he gave the appropriate numbers of 5, 4, 3, 2, and 1. So later astronomers put a number on the difference in the brightness between star 1 to star 2. And they said it was 2.512. So that means that star 1 was 2.512 bright as star 2. Star 2 is 2.512 as bright as star 3, and so on. So you can see there's 5 intervals between each star, 1, 2, 3, 4, 5. So that means if we raise 2.512 to the 5th power, multiply it by itself by times 5 times, then we're actually going to get 100. So that means that there's 100 times difference of brightness between star 1 and star 6. So let's go to this next slide to describe this a little bit further. Here we have our magnitude scale with 0, and if we went from 0 to 6, we would be 100 times as bright. And astronomers gave certain apparent magnitudes to different objects in the sky. For example, the sun has a apparent brightness of minus 26.4, and the moon has an apparent brightness of minus 12.4. So there's 14 magnitude difference between the two. So if we took 2.52 and raised it to the 14th power, we would get over 400,000 times as bright. So the sun is about 400,000 times brighter than the moon. And then we can look at really faint objects. For example, if a star has a brightness of 30, which is very faint, the Hubble telescope can see it. And typically our naked eye can see anything up to about 6. So again, this is where we're talking about the apparent magnitude. So let's go and talk about the absolute magnitude by looking at this picture. And what this line represents is 10 parsecs. Okay, so if we look at the sun in the sky, we're going to say it has an apparent brightness of minus 26.4, right? But let's say we saw this supernova explode, and the supernova is right here, and it actually, we saw this light up in the sky. We didn't, but the Chinese did in the year 1504, July 4th, 1504. And the apparent brightness, according to the Wikipedia page, was minus 6. So its apparent brightness was less than the sun at minus 26.4. And if you look at it, you can see it's not quite as bright as the sun. But that doesn't mean that supernova is any less luminous or less energetic than the sun. In fact, it's about billions of times more bright than the sun. And the way we can now look at that is by classifying the absolute magnitude is to level the playing field by moving both these objects at the same distance, which is this 10 parsecs. So we're going to move the sun to 10 parsecs, and we're going to move this supernova to 10 parsecs. And now astronomers will measure the magnitude at 10 parsecs. So it's actually like measuring the apparent magnitude at 10 parsecs. And we're going to get, for the sun, an absolute magnitude of 4.83, which is much fainter than the 26.4. And for the supernova, we're going to get an apparent or absolute magnitude of minus 19.3, which I just took as the absolute magnitude for most type 1a supernovas, which we'll go over in another video. But now there's a large difference between the brightness at minus 19.3 compared to 4.83. So if I took our 2.512, and the difference between 4.83 and 19.3 is 23.83, and I did that on my calculator, and I got, like I said, approximately 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3.6 billion times as bright as the sun is what a supernova is. I hope that helped clear up a little bit on absolute and apparent magnitude, and we'll see you in another video. Thanks.